So hi there, this is a video about a timer component. This is the NE555 timer. And this particular 555 timer and the datasheet we are looking at is from Texas Instruments, I want to mention. And now for the fun part, how does this work? Let's look at this datasheet. So you see on the left here this resistor RA. And if you go down, you see the resistor RB, and then you see this capacitor just before ground, which is symbol C. These three very much determine how this thing behaves. Now, to say a general word, you put a random input voltage at the input, which is here VCC marked. And you see it can be from anything from 5 volt to 15 volt. For the functioning of the circuit of the 555 timer, it does not matter. And then you get at the output some special kind of waveform, and you see that on the right, and you get such a square wave, as you see. The square wave voltage output, see it has high, then it goes low for a shorter time, high, low. And these high times, the times the voltage signal is high and the time the voltage signal is low, you see they can be different, and they are called small th here in the drawing to the left of the squares. And here small TL, so TH for T high and TL for T low. And you can adjust that, how long it is high and how long is low. And we'll see that on the next sheet because of the data sheet, because it really only depends what you put in as RA, resistor A, on the left picture, and what you put in as RB as resistor B and C. And by changing these three components, you can adjust the shape of the output waveform. And it's a cool thing. It's a kind of an oscillator you produce just by having such a 555 timer. And it's a cheap component, and you can feed it with, for example, like here 5 volts. And you put in 2 resistors and a capacitors, and boom, it swings, and it's cool. So let's see on the next page of the datasheet how exactly what kind of waveform we can produce here. So basically, these two formulas are the core concept. You see the time the signal is high of the pulse is this range 0.6 something. I call it 0.7 just for sake of a joke. And then you add the two resistors together and you multiply it by the capacitors. And the low time of the pulse signal is also similar, but now we have our 0.7, and then only the B resistor determines in conjunction with C how much the 555 timer is low. So you get, if you want to say it in relation to each other, you say RA and RB in sum determines how long the signal is high, and RB alone determines how long the signal is low. So if we look at the x-axis of the diagram to the right, it says there is the capacitance in microfarad given. And so I have a capacitor here that is 100 nanofarad, and that is 0.1 microfarad. Like I can put the orange box around it. And now let's combine two resistors that I have. Let's say two 1K resistors. And so we are at RA plus RB 2 kilo ohm. And then we should land somewhere in between. Yeah, right, somewhere in between. Luckily there's a formula. If you look here to the left, it says what the frequency is, and we can calculate the frequency after this formula, 1.44 over, and our RA is 1000 because it is a 1 kilo ohm resistor, and our RB is also 1000, and our C is 100 nanofarad, and that is 10 to the minus 7. And if we calculate this mathematical fraction, then there comes the result 4800 hertz, which is 4.8 kilohertz. Can you imagine 4800 times swinging per second? What can you do 4800 times a second? I can't. So that's amazing. And of course, we want to do this circuit now in practice. Just before I say it's really magic, I take a 1K resistor, it's your average off-the-shelf resistor, and you take another 1K resistor, your average off-the-shelf resistor, and then you take a 100 nanofarad capacitor, you have that lying around, and you just put that together and it swings with 4.8 kilohertz. And now let's go to the bench and do that. But of course, in reality, we have no real 1000 pure resistor, but I've picked here two. The first one you see is 994 ohms. The second one is 997 ohms. And the capacitor is 105.1 nanofarad. And I measured these with my digital multimeter. And so here you see that I have calculated the frequency with those real values of the components. And it is 4585 hertz, so 4.5 kilohertz, 4.6 kilohertz, and not the 4.8, but yeah, close enough. And as you see here, I have it all put together, and I have here a power supply switch, which I can turn on. It's now off. You see there's no waveform, and then let's switch that thing on. Tuck. And now the lights are green, and there is our waveform, and we have 4.61 kilohertz, nearly exactly what we predicted. It was around 4.58. And if you're looking at the average here, it says on the frequency statistics it says 4.60, so it's even closer to our calculations with the real values. So thank you, that closes the video. I hope you enjoyed it, and I'm looking forward to share with you in my next video.